The band model. The electronic band structure describes the conductivity of conductors, insulators, and semiconductors. It consists of two energy bands, that is, valence and conduction band, and the band gap. The valence electrons, which serve as charge carriers, are located in the valence band. In the ground state, the conduction band is occupied with no electrons. The ground state of an atom is the stationary state of the atom with lowest possible energy. When an electron acquires enough additional energy, it can leave the valence shell and become a free electron, and then it exists in what is known as the conduction band. The difference in energy between the valence band and the conduction band is called a band gap or an energy gap. It is a region in insulators and semiconductors where no electron states exist. The width of band gap affects the conductivity of materials. In order to achieve a conductivity, electrons from the valence band have to move into the conduction band. Now, look at this figure. It shows energy diagrams for insulator, semiconductor, and conductor. This is the band model of insulator. In insulators, the valence band is fully occupied with electrons due to the covalent bonds. These electrons cannot move because they are locked up between the atoms. As you can see, the band gap in insulators is very large. This band gap can be crossed only when breakdown conditions occur, that is, when a very high voltage is applied across the material. Now, look at this band model of semiconductor. In semiconductors, the band gap is smaller, which allows an electron in the valence band to jump into the conduction band if it absorbs a photon. This band gap depends on the semiconductor material. Now, look at this band model of conductor. In conductors, the conduction band and valence band overlap, so there is no gap as shown here. This means that electrons in the valence band move freely into the conduction band, so there are always electrons available as free electrons. Now we will compare a semiconductor atom to a conductor atom. We know that silicon is a semiconductor and copper is a conductor. Bohr diagrams of the silicon atom and the copper atom are shown here in this figure. As you can see, this is core. This core includes everything except the valence electrons. Note that the core of the silicon atom has a net charge of +4. It means there are 14 protons and 10 electrons in this silicon atom. The core of the copper atom has a net charge of +1. It means there are 29 protons and 28 electrons in the copper atom. The valence electron in the copper atom feels an attractive force of +1, whereas the valence electron in the silicon atom feels an attractive force of +4. Therefore, there is more force trying to hold a valence electron to the atom in silicon than in copper. The copper's valence electron is in the fourth shell, which is at a greater distance from its nucleus, as you can see here, whereas the silicon's valence electron is in the third shell. We know that electrons farthest from the nucleus have the most energy, so the valence electron in the copper atom has more energy than the valence electron in the silicon atom. It means that it is easier for valence electrons in copper to acquire enough additional energy to escape from their atoms and become free electrons than it is in silicon.